Hello, boys and girls. So I was engaging with Bayesianism lately, still in the context of diffusion models, but I was tinkering with the propositional logic of Bayes' theorem if you promote it to be, a statement talking about implications. You have conditional probabilities given a B holds with a certain probability, and Bayes' theorem has some logical implications. I was working them out a little bit for myself, and I was going to make a video on that. But then I thought I have not really talked about Bayes' theorem explicitly. I think in this video I will, in years to come, certainly at one point talk about like Kalman filter and a little bit control theory. And maybe I do a theory video to reference Bayes' theorem and some implementation. So in this video, we are going to go through some simple examples. And I have, sometimes I do, some implementation. You can tinker with it, you can extend it, you can learn probability with some hands-on examples. And I will implement Bayes' theorem, the update step basically, and explain it with some examples. The one example, because I think people know it, this is this 3 blue 1 brown video where it's about some test and it has some chance of having false positives, and then you get out here there's these numbers, and we will sort of recalculate that. I will give you the script or plug in the numbers, and then you get you validate basically what is said here in this video. But a little bit more elaborate example. I went to the library, got this book just to get to an example. There's another sort of medical example with a little bit more data points. And I show you how that works. So we will discuss this code in a second. If I run it, then it samples some random data and gives us a nice plot. So this is basically the outcome of the script. So in this case, just to shortly explain it, you have let's say a random variable, and this can have certain data points under consideration. So these are these black points. They all belong to this variable. Let's call it x. And before the Bayesian update step, you have some probability assigned to it. So this line here that I follow now, this is sort of the before the measurement probability that you assign to different values. For example, here this is roughly 0.5, and you assign a certain probability that this random variable has this value, and you assign a certain probability that it has this value and this value, and then you make a measurement. In this case, this gray line tells us from the plot where the measurement was, and then suddenly the probability, your credence in this Bayesian sense that you assign for the actual value being here is much higher, and so there is here some gain in the probability, and other values are penalized. And then whenever I run the script, then it draws a similar graph but with a little bit different numbers and gives us a nice plot, right? So here's another example. So here again, there's different values that can be taken, and then there's a measurement around 0.3, and when before the darker lower line was like more or less even probability for all these values, then after the update, the Bayesian update, you think that it's more likely to be here and not here. Okay, so this is the script that we'll write, and I on purpose coded this is in a sort of generic way. You have bit data or hypothesis, hypothesis. What is the English phrasing? And so you have a little bit of code which is very simple, which can apply to both this 3 blue 1 brown example and some more generic serious data here. Okay, so with that said, let's get into it. I will skim over all the plot implementation and some of this printing stuff, and focus on the math, so to speak. I import the random because, as you just saw, I random sample some data for this plot. I use this SciPy just because it has a binomial coefficient function, although this is very simple to implement as well if you can do factorials, plotting library, and then a little bit NumPy to normalize and component-wise multiply. I have here a normalization function which just takes any list or more fancier stream and normalizes the values so that if you sum over all the values, you get 1. And then we have the main code implementation, which is really just, you can write it in 1 line. Here I like described it a little bit and wrote it in 4 lines, but it's very simple. So we are going to implement a function which with an index I, you have an indexed list of HIs, the hypotheses. These are these things. And we assume we have a prior probability assigned to all of them. And we pass into this update function a likelihood function. I will describe it in a second. And then a measurement value. And what this function does is it returns another list, which is of the same length as the prior. So another probability assignment to various hypotheses. And this will be the changed probability. So if I run the script again, right, just so we see the terms here. So in this plot, if you compare with the inputs of this function, there is like a bunch of possible values for the hypothesis. So all these points, red off on the y-axis, are possible values for HI. So this is the first H, the second H, the third H, and these are the possible values that it could take. We have for each of those possible HI values priors, which is this darker blue line here. So this is a probability distribution, right? So the integral over this probability distribution would be 1. We assign some probability. We pass a certain likelihood function. The likelihood function really depends on whatever model we have. So in this case, it makes sense, as we will see for this example, that it's like a binomial distribution that we use for giving a probability that given any of the hypothesis values, a certain measurement is to be expected. This is sort of the ingredient. This is sort of the modeling part of the situation. And then we have a sort of we have a sample and observation, or this is all like equivalent words. The x value. In this case, I make the x value with this gray line here. So in this case, the actual measurement is around 0.7. And then what this function does is it implements the Bayesian update and returns the posterior. The posterior is this light blue line, another probability distribution summing to 1. And in this case, because the measurement was here around 0.7, these three values are suddenly much more likely, and that's why the probability distribution is bumped here. And like at the same time, these values before it or after it are penalized. Okay, so this the return value of this update step is a list. So in MathSpeak, that is a function from an index to the element of the list, and the element that is returned is another probability. So given the fact that this measurement is a fixed value x, right? You should not consider this a variable. This is like a fixed value that is passed to this function. Therefore, the x here is fixed, and so what is returned here is really a probability for all the I, like the hypotheses which are indexed by I. And so the parameter, this is base rule, all these objects are exactly the things that we have to pass in. And this is more or less, wait a second. So P, this is the prior probability distribution. This is the likelihood function, which has to be modeled, as I said. And then we pass also in all the possible values, because we put in a list and return a list. And I said all these pass to it. This thing, the last p of x, the probability for the measurement, the marginal probability, we don't have to pass in, because this is computed automatically if we normalize. If we wanted that the return value here is a normalized probability distribution, then we can just take the numerator here and normalize, and this is returned. So this is the implementation. Okay, what happens? So first we compute this thing for all the h values. You see this loop here. Then we for each h we compute this product. This is this numpy multiply, like component-wise multiplication of the likelihoods and the priors. And then we normalize, and this is it, right? This is an implementation for our purposes here of the base rule. Okay, now we already have done the main thing, and now come the examples. So, you can go to this 3 blue 1 brown video. You can watch it. The important thing for this video is around 3 minutes here. I will not go through this video, because I don't even know how the sound will be if I start it now. But basically what you have is, he discusses that the situation with breast cancer, and you have a breast cancer test, and these tests are they have certain quality to it. If you measure and you have breast cancer, then 9 out of 10 times it would actually give the right result, but sometimes it gives a false negative. So it gives the wrong result. It claims you do not have breast cancer despite you actually having it. So there's this 1 out of 10 chance that it is wrong in this way, and then there's 98 out of 910 or whatever number he makes up for this video. There's another chance that you have a false positive, meaning it tells you yes, you have breast cancer despite not actually having it. So you have these error cases, and then he has this, this is like a standard or surprising result. You use Bayes' theorem, and it tells you that because how the numbers are, if you make the test and get a positive result, the chance that you actually still have breast cancer is actually super low. It's just 1 over 11, and that's because the base rate of people who actually have breast cancer in the population is so small. Okay, watch the video if you want to see this more. But here, my implementation. So it is always the case that the main ingredient is to design the likelihood function. Given a hypothesis, finding out what is the chance of having an actual measurement. In this case, the hypothesis values are either you are sick or not sick, or have breast cancer, or does not have breast cancer, and the observation is the test result. And as you just saw there, there's these 2 values made up by 3 blue 1 brown for this example. If you have breast cancer and you make the test, and the chance of then actually getting positive results, meaning yes, you have breast cancer result, is 9 out of 10. While if you don't have it, there is still this sort of almost 1 in 10 chance of getting the wrong result, or whatever the fraction is here. And so what is the implementation of the likelihood situation in this case? Well, there's only these 4 cases that you have to consider, right? You have it, you don't have it, you get this result, you get that result. And so here you see the implementation. I define this these 4 values. If you take if you take any of those and flip it over, then you have the other chance, right? There are certain probabilities that always must sum to 1, so the other values are always 1 minus. And then there's these different situations. I introduce a boolean here that the test claims that you're positive, meaning the test value is sick. And then there's other boolean that says that the test is correct, when the test result is actually the underlying value, the possible age. And then depending on these two bools, there's for probabilities that could be returned from this likelihood function. I also, there in statistics, there's this sort of statistics which scientists or whatever in all fields make, and they like their p-values, which are also sort of a certain conditional probabilities. There's a certain language that actually, when I studied physics, and we basically don't use this language because we use just the mathematical terms. But it's good to know them, what this and that is. So I've commented it here, null hypothesis and type 1 error and these kind of things. So I just translated it here and give you this sort of glossary. Okay, and so having implemented that, likelihood function, the main ingredient, I do a test and check that the value that is here stated in this 3 blue 1 brown video, this is the example result. If the test is positive, what is the chance of actually having cancer? Oh, it's only so small. I do sort of a unit test and test against the value that is claimed here, and this function I use below in the script and test it against floating point precision. And indeed, the script doesn't crash, so my implementation of Bayes' theorem here was correct. There's a printing function where I explain this sort of medical story, and it's also what you see here. I will not go through it, but because I just explained it. But this is for the script, and then I have my example here, and that's how it's here implemented. This is the whole implementation. So if I run this main function, there is the base rate, and this is also then used as a prior of how many people actually have breast cancer. In this case, in this numerical example, the numbers chosen is 1 out of 100 women has breast cancer apparently. And if you would have to say, if you pick a random person and say, does this person have breast cancer, the chance that she has is, or he has, I guess it's only women in this case, it's 1 in 100. And then if the same person does the test and gets this and that result, the question is, what is now your updated belief? The hypothesis, the possible options here are being healthy, being sick. So this is Python implementation to get the keys. And the priors are the priors are this normalized. Apparently I didn't write the normalization function, but my implementation automatically normalizes. So maybe I should just just for the sake of not confusing anybody, I will add this normalization call here, so that they are actually probabilities. But this is just because these are the values. The priors here are the values 99 and 1, and not 99 over 100 and 1 over 100. So okay, and then I compute all the posteriors, and because there's basically 4 options, right? What the actual ground truth is, the underlying value, and what the test returns. I have this sort of 2 for loops I implemented with a zip and with this dict loop. But this is just the application of the update value to all these values. And then I take this and do the check for the 6-seed situation, and it does not throw the assert, so everything's fine. And I have this story that you see here. You can read it if you really want, but everything works out. Okay, so the implementation works in this case. And now the more interesting case, again, I will run it again. This is now the other example. This is literally taken over, stolen from this book. Maybe I can even close to the introduction. I will pull this out here. I hope this is nice SMR. So in this case, there are some. I'm not really sure if you can read this at all, but there's some table with some numbers, and it makes up some priors and some values. Can you read this? Probably not. Sorry, not very well organized the video. This is here. It has like some fixed numbers and explains sort of this example. It does not sample random numbers. I think they discuss programming language in this book, but as is often the case from these 90s books, they have like some obscure language which completely fell out of favor, which sort of takes up space in the book. I tend, if the scripts are always small, I tend to not need or want this sort of implementations, because you can just take the math and implement it in most cases anyway. But okay. What is the situation? I will explain in words what the situation is there. So in this situation, you, like in the book example, you have also a population, and there is a certain number of people in the population who have a certain feature. Let's say also like a sickness. A certain number of people in the population is sick. And let's say I don't know, 7% or so are sick in the population, and then there's a bunch of studies in this narrative, in this story, which all like the underlying true fraction of people who are sick is like 7%, but there are a few studies and statistics has been computed or estimated or whatever, and all the studies give some value. So one study says, or there's actually 10% of people are sick, and others says only like 8 are sick, or another study says only 4.4% of the people are sick or whatever. And so you have the certain discrete values. These were in the plot drawn on the let me actually make another plot on the Y line. So here there's a lot of studies, like in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 16 or so studies have been proposed. They have, in this case, wildly different values, but it's just for visualization. And there is an a priori credence that the researcher gives to all of these studies. So a priori, we see that this is the highest value a priori. To the value around 55% or whatever. This is like considered most likely. And then what the researchers do is they do their own like sort of sampling, and you say we are sampling 30 people, and then we check how many of those have the sickness. So there's a certain ratio. Let's say you get back 4 out of the 30 people were found sick. This is your measurement. This is your X. And then what you do is, in the likelihood situation, you say, if the probability if the number of people, the hypothesis is true, that is 21%. If this value is the true value, then what would have been the chance that exactly 4 out of 30 people were found to be sick? So there's this the question, if this value is correct, then what is the chance of obtaining the measurement that I just obtained? Okay, and to do that, I will not, this is like basically combinatorics or basic probability theory. The appropriate thing to use here is this binomial probability, namely, like here you see the implementation. You have this proposed rate, this hypothesis R. Let's say it was this 21%. And then from these 30 people, like n is 30 and k is your finding of 4, the chance that there's exactly 4 people who got that you pulled with the sickness in a row is like the rate, the power of k, right? And the others must have, you know, been found not to have the sickness. So you have 1 minus r to the power of everybody that's left. So again, I will not like explain this, but maybe you followed and it makes sense to you. This binomial distribution is sort of the go-to thing for a lot of like yes/no problems, and gives you this likelihood for certain proposed rates in a population, and you make this sort of binary tests there. So this is the chance, and you know, weighted with all the possibilities of this having been obtained. That's why I imported this binomial library, and yeah, and then you return that. So this is all the possible ways that given this rate you could have made this observation that you just did. So this is the likelihood function, and this is the main ingredients. I already said, you know, we are going to sample random prior probabilities, like credences to all of these different studies, and so basically you know what the rest of the script is going to be like. There's another scripting function. You can look at it in the GIST. I will not explain it, but this is sort of the narrative that I explained in words now. And there's a nice plotting function. You know, I think the plotting function turned out very nice, but I will not discuss it. This is like, you know, this terrible matplotlib library, which I hate. But you know, at this point you can just use ChatGPT to have it plot everything for you. Although I tinkered with this on my own, so you enjoy the plots. And here is the example that I describe. So what I do is I sample the possible study values. You know, the rates. What I do is I sample them from a Gaussian and throw everything out this, because it's a rate that's under 0 and over 1, right? So this is just how I generate the random number. I deal with a priori 15 values, although I cut out whatever doesn't make for probability. So this is just, you know, my some magic constants for making this plot and sampling some data. These data, you know, these H's in this case are the proposed rates, the proposed probabilities, these are sort of a fraction of people in the population which have the sickness. And then I also random sample some probabilities for them, right? This is the curve, that the probability I assigned to everybody. By the way, what I do here is I take the random data, these rates, the black line, and you might have noticed that I sort them here just to get a nicer plot, right? I sort these the proposed rates in the studies in ascending order, so that these like make a nice, like, all possibilities, they grow up, and I do not order the probabilities. You know, this is just the matter in which you do the graph. There's no inherent order in the studies. I just sorted them in ascending order. So this is just this sorted call here. Okay. And yeah, then I sample the value, you know, in this case, you know, k out of n. We here use this random the library. This is the gray line in the plot. Then I have my sample. Then I use the update priors function, the implementation of base rule, and then I have another distribution and I plot it and I'm done. This is the implementation. So this is the script. I will execute it one last time. I hope my explanation was coherent. So again, you know, here's the different studies. They have different probabilities. Is this darker line here. The measurement is made. I find that in my own measurement, 30% out of these 20 samples in the population have it. So this value, or all these study values around this become much more likely, and so the posterior probability has gone up here and has gone down further on the outside. Okay, I'm under 30 minutes, so I will leave it at that. I hope that helped, and the next video will be about propositional logic and its relation to Bayesianism. Take care. Have a nice weekend.